Hello, my name is Cooper Myers, and this is my graduate project for EE566 Engineering Optics. The paper I will be covering is Miniature Solid-State Laser for Space Applications by Bhavana, Patty, and Kenneth Stebbins. This is a conference article that briefly covers the process, design, and results of such a laser. The goal of the research is to ascertain the usefulness of a small-scale solid-state laser. When creating a laser this small, it is important to keep note of SWaP to ensure that its size and weight are optimal for the power generated. Additionally, the efficiency of the laser must be kept in mind. The laser was designed with two pump diodes spaced 1 mm between a 24 mm ND YAG crystal. The output of the pump diodes is aimed at the side of the crystal, which is cut at Brewster's angle. This creates a high degree of polarization purity within the beam, ensuring there is very low reflective loss when passing through the crystal. Once the laser is amplified to the desired output, it is passively Q-switched by a CR YAG crystal at 25 Hz. The CR YAG is a saturatable absorber, meaning that once the gain reaches a certain loss level and the pulse has built up, i.e. the absorber is saturated, its loss is reduced, further accelerating the pulse buildup. This means that every 0.04 seconds, the absorber is saturated and then creates a pulse as its output. The output coupler and mirrors were fixed to align the laser. Then, the optical components were soldered to a goniometer for precise alignment of the laser resonator. The first image at the top of the page shows the process that was just described to produce the laser output. The image below shows what a goniometer looks like. A micrometer is used to adjust the degree of rotation with a small angular range, which is the knob on the left side of the image. To the left is the ray tracing of the pumped light. Each diode has 3 bars that provide 900 watts of power. The image shows where the most optical amplification will occur in the crystal, around this section where the green and blue are very intense. The right portion of the same image is the cross-section of the pump's distribution inside the crystal. Here it is seen that the most optical amplification will occur near the center in the dark blue portion of the image, right about there. The image on the right shows the housing of the laser. The case is made of copper tungsten and its dimensions are 70 by 32 by 28 millimeters. The results of testing the laser are shown to the right. The laser's output was 6 millijoules of 1064 nanometer energy with a pulse width of less than 4 nanoseconds. The m² value was less than 1.5, meaning the laser has a high quality. This output was frequency upconverted using a lithium triborate nonlinear crystal, which resulted in 3 millijoules of 532 nanometer energy with a pulse width of 3.6 nanoseconds. This is a 50% conversion efficiency. The process of upconverting a laser is passing 2 photons through a nonlinear optical element where they interact with each other, annihilating each other. This is effectively combining and creating a new photon with frequencies that are the sum of the original 2 frequencies. The image shown on the right is a single-shot pulse width and beam profile of the laser. The pulse width is measured at 3.8 nanoseconds. In the upper corner of the image, a measure of the intensity of the beam is shown. The next steps for the miniature solid-state laser are to improve its output or to alter it to specific needs. The laser was built in a modular manner, making additions easy within reason. To create third and fourth harmonics, a second stage of conversion optics can be added. For a higher energy output, more pump diodes can be added to the structure. For more power, an additional amplifier stage could also be added. Finally, if other wavelengths were required, such as infrared or UV, other nonlinear crystal elements can be substituted. The image present on the right shows the beam getting frequency converted from 3 to 6. This could be done by inserting a different nonlinear crystal. Finally, the applications for this laser are best seen in laser-induced breakdown spectroscopy, LIBS, and Raman spectroscopy. The image on the left shows the process for LIBS, where there is a laser light directed at a small area of the surface of a material. This causes the material to rapidly vaporize and ionize, forming luminous plasma. When the plasma cools down, it emits lights which contain information about the composition of the material. A spectrometer is then used to analyze this light. Raman spectroscopy is where a light source In this case, a laser is directed at a sample where few photons from the laser interact with the material. Most photons are scattered without any change in energy, but some undergo Raman scattering. This is where the photons excite the molecules to a higher energy state, and when molecules return to their ground states, they emit photons with energies corresponding to the difference in energy levels. Like LIBS, a spectrometer separates the emitted light into its constituent wavelengths and measure the intensity of each wavelength. These types of spectroscopy can be used for elemental analysis of rock samples. For medical applications, the laser could be used for glaucoma surgery, where the laser could be used to open up drainage tubes within the eye. This drains fluid built up, thus reducing pressure inside the eye. Thank you for listening, and here are my sources. Once again, thank you very much.